In this video, I will be going over section 2.1, area between curves. So the concept of an area of a region between two curves is very similar to the idea that you learned in Calculus 1. And that is that you had a graph of a function between 2 points on the x-axis, a and b, and you wanted to find the area underneath the curve. All right, and if this was function f of x, we learned that we would take the integral from a to b of f of x dx, and that would be the exact area underneath that curve. So the idea that we're going to be working with today builds on that idea. So let's get rid of that. So we have two curves now. We have f of x, and again, we could say, okay, the area underneath the curve of f of x dx, which would be all of this area in here, could be found with that integral. If we wanted to find the area underneath g of x, which is right here, we could do the integral from a to b of g of x dx. And that would give us all of this area underneath here. Well, as it turns out, the area that we're really interested in would be the difference between those two. If we were to take the area underneath f of x and subtract the area underneath g of x, we would have this area in here. So we would take this minus that, and that would give us the area between the two curves. Kind of an intuitive way of developing this idea. Well, let's look at a more mathematical way of looking at it. So back in Calc 1, you learned that we can take the area underneath the curve, and likewise, we're going to take the area between the two curves and break it up into a series of small rectangles. And so the width of each one of these rectangles is delta x. And we'll make each rectangle the exact same width. Makes it easier that way. Well, the height of the rectangle goes from here to here. And so the height of the rectangle is basically f of x minus g of x, the difference between those two values. Now, f of x is where the rectangle intersects the function f, so it's the function value there. And g of x is where the bottom of the rectangle intersects the function g of x. So this is going to give us the height of the rectangle. So the area of the rectangle would be equal to f of x minus g of x, that's the height, times delta x. That's going to give us the area of this one rectangle, all right? Well, we want to know the area of a whole bunch of rectangles. So here's our formula right there. Okay, that's the formula. Well, to find the area of all of these rectangles, we create what is called a Riemann sum, which means we add up a whole bunch of areas, and so we use the sigma notation. And so the area is approximately equal to the summation from rectangle 1 to rectangle n, however many rectangles there are, let's just say 10. We're going to add up 10 rectangles. We're going to take the difference between f of x minus g of x and multiply it by delta x. Well, the next step in that's going to give us an approximate area. If we wanted to find the exact area, we learned in Calc 1 that we can take the limit as the number of rectangles approaches infinity. And so we take the limit of the Riemann sum, and we have an infinite number of rectangles, and that gives us our integral. And so the integral to find the exact area between two curves is the integral from a to b of f of x minus g of x dx. So let's take a look at that and compare it to what we did intuitively before. So intuitively, we said, well, the area of f of x, we can break this into the integral from a to b of f of x dx minus the integral from a to b of g of x dx, just using our some properties of integrals that we learned once before. And so the integral of f of x dx minus the integral of g of x dx, that's exactly what we had up here from a more intuitive point of view. All right, that's pretty much the formula that you need to understand to do today's problems. So I've already done the problems in my notes. What I'm going to do is I'm just going to go through. So here's the formal definition from the textbook. And so let's just take a look at problem number 1. If R is the region bounded above by the graph of the function f of x equals x plus 4 and below by the graph of the function g of x equals 3 minus 1/2 x over the interval from 1 to 4, find the area of region R. So the first thing I like to do is go to Desmos and graph this in Desmos. And so that's what I am going to do now. So here's Desmos. I've already graphed y equals x plus 4. And now I'm going to put in my second function, y is equal to 3 minus 1/2 x. So I'm just going to do 0.5x. And so we're looking for the area between those two curves. And my bounds of integration, there's many different ways you can do the bounds of integration. One quick way to do it is just put in an x equals, the left bound is 1, and then x equals 4. And so there we have our region. All right, so the top, the left-hand side of the region is right here. The right-hand side of the region is along the green line. Those are our left and right bounds, our upper and lower bounds. And then we're bounded on the top by the black line, which is y equals x plus 4, and the bottom by 3 minus 1/2 x. So from there, make a sketch. It doesn't have to be a great sketch, just a little bit of a sketch on your paper so that you can see what's going on. Label the graphs appropriately. So we have this is that graph right there. And then we have this line down here is g of x. And the area that we're looking for is this area in here. So we graphed using Desmos, drew a sketch. The next thing I like to do is set up the integral. All right, setting up the integral is the important part of this problem. And so here is the integral being set up. If you set up the integration problem correctly, you're 90% of the way there, because the integration itself is not going to be too difficult. So let's just see how I set this up. First of all, we did the integral from 1 to 4. Those are my left bounds and my right bounds. And then we have to have the curve that is on top. The curve that is on top, which is x plus 4. Minus the curve that is on the bottom. And the curve that was on the bottom was 3 minus 1/2 x. It's always the top minus the bottom. Top minus the bottom. You have to know which curve is on top and which curve is on bottom. And it won't always be the same. And it may switch. All right, then simplifying that a little bit, we end up with the integral from 1 to 4 of 3/2 x plus 1. And then it's just a matter of integrating it from there. And so nothing tricky about this integration. 3/2 x becomes 3/2 x squared divided by 2, or 3/4 x squared. And the integral of 1 is x. We are evaluating that from 4 to 1. We end up with the area is equal to 57/4. Now I'm going to show you a nifty way that you can check this using Desmos. And so to do this, let's go back to Desmos. I am going to actually enter, I'm going to write INT. INT gives you the integral sign. And we are integrating from 1 is my lower bounds. My upper bounds is 4. And then let's put a parentheses in here. Parentheses. Actually, we need 2 parentheses. My upper x plus 4. I'm doing this on an iPad, which I'm not really used to doing. Minus 3 minus, and let's do the 0.5x again, paren and another paren, and then want a dx. Boom. Now notice when you set up the integral correctly, it's going to give you a number. It gives us 14.25. 14.25 is telling me that this is the area between these two curves. Well, how do I know that my answer is correct? Well, the answer that I got was 57 fourths. So let's see what 57 fourths is. 57 divided by 4. No, that's not right. 57 divided by 4. Oh, that's better. 14.25. So you can use Desmos to actually set up an integration problem. And I actually encourage you to do that. In WebAssign, you're usually going to have to give algebraic answers. But you can then calculate those algebraic answers. You can convert them into decimals to see if you got the work correct. So on exams, you're going to need to show work. And when you show your work, you're going to have to set up the problem correctly. And again, that's half the battle. Okay, so that is the first problem. Exercise number 2. Okay, exercise number 2 is similar. Find the area enclosed by y equals 9x minus x squared and y equals 2x. So go to Desmos, graph these equations. I'll go and graph this one as well. Let's get rid of all of this. And so let's just do y. We don't need to use functional notation. We can just use 9xy. Whoops. We can use y instead of f of x or g of x. Y equals 9x minus x. And use the a to the b power if you're using an iPad to the second power. All right, there's our first equation, upside down parabola. The second one is 2x. So we have y is equal to 2x. And so we're finding the area enclosed by. They're not giving us any bounds. So what we need to do is we need to figure out what the bounds are. So when it says find the area enclosed by with no bounds, we need to find an area that is completely enclosed by these two graphs, by the line and by the parabola. So this area from up here all the way to down here, and then up the blue line, up the blue line. And so if we go back to here, here's a nice little drawing of what that area going to look like in through here. Now we need to know where these two points of intersection are. Well, you can find those algebraically, or you can use Desmos. Again, Desmos is really nice. It tells you what this point is, 714, and down there, the point 0, 0. Go ahead and use Desmos. But if for some reason you need to do it algebraically, you should be able to do that simply by setting the two equations equal to each other and solving for the values of x. Good old-fashioned algebra. So now we need to figure out what is the function on the top, what is the function on the bottom. Well, the function on the top is the upside-down parabola, which is 9x minus x squared. So that's going to be my first function, minus what is on the bottom, which is the line, which is 2x. So we have the integral from 0 to 7 of 9x minus x squared minus 2x. Simplifying that a little bit, always simplify first. Always, always, always simplify. It makes integrating easier. The more you can simplify, the less terms you have to integrate. And then from there, we just use the power rule. So 7x becomes 7x squared over 2. And minus x squared becomes minus x cubed over 3 or minus 1/3 x cubed. I always like to write the fractions out in front. Makes using the power rule easier. And then we're evaluating all of this from 7 to 0. So plugging the 7s in, plugging the 0s in, subtracting them, you end up with 343 over 6 or 57.17. And again, we can check this using Desmos. And so let's just do that for the fun of it. Let's enter in another integral. To get it started, you start typing INT. And so my lower bounds of integration is 0. And then the upper bound of integration is 7. And then we want to do 2 parentheses. The whole thing has to be in parentheses. And then the first term in parentheses. Always enter your original integral as it is set up before you've done any simplifying. That way you know you've set it up correctly. So x squared. So 9x minus x squared minus, and then in another set of parentheses, 2x, and then n paren, and do not forget to actually type in dx. It doesn't know what you're doing until you put that dx in there. So we have 57.16 repeating. Now let's just see if our answer was correct. We got 57.17. Or we got 343 thirds if you wanted to do it that way. So 343 divided by 6, and we got 57.1666. So we're good. The last problem I want to do in this set of notes is exercise number 3. Find the area bounded by y equals 5 over x, y equals 10 over x squared, and x equals 6. So go to Desmos, graph all of these. So let's do that. Let's get rid of all this. And so my first equation is y equals 5 divided by x. Whoops. It doesn't look right, does it? Y equals 5 divided by x. And the other equation is y equals 10 divided by x squared. And the third equation is just x equals 6. So that's going to be a vertical line. Let's see what we're looking at here. So let's expand this. It looks like we're looking for the area that is underneath the black line to the right, to the left of the blue line, and then above that line. So in this area, which function is on top? The function that is on top is 5 over x. So back to my little drawing. That's exactly what I have here. I have 5 over x is the function that's going to be on top. And then 10 over x squared is the function that is on the bottom in this region. And then, of course, we've got 6. So we're looking at all of that area in there. It's important to get a good look at what you're doing. All right. So the bounds are from x equals 2 to x equals 6. Well, clearly the right bound is 6. And, of course, we just found the left bound in Desmos. That's the point right there. That's the point 2, 2.5, where the point of intersection. You could also set the two equations equal to each other and solve it algebraically. So the left bound is 2, the right bound is 6. And so the function that's on top is 5 over x minus the function that's on the bottom, 10 over x squared. And so here is my original integration problem set up. That's what I'm going to enter in Desmos to check my answer. Actually doing the integrating, remember that 5 over x, the antiderivative of that is 5 log of x. And so the x squared in the denominator, we bring up to the top, make it x to the negative 2. So negative 10x to the negative 2, when we apply the power rule, is 10 over x. Evaluated from 6 to 2 gives us all of this, which simplifies to this. And this is the answer you're probably going to end up writing in WebAssign. How can you check to see if that answer is correct? Well, let's go back and do this again in Desmos. So we're going to type in int, and we are integrating from 2, and the upper bound was 6. And so let's put, I only need one set of parentheses here now. So we have 5 divided by x minus 10 divided by x squared. So x squared dx. Don't forget the dx. So we get 5.15. Well, let's write our algebraic answer, 5 log of 5. Let's see, 5 times the log ln, I think it'll recognize that, log of 5. Yep, it does. Minus 10 divided by 3. 4.5 log of, 5 log of 3, not 5 log of 5. Gotta be careful. 5 log 3 minus 10 thirds. And so those do not agree. So something is wrong. Oh, and that's because back up here, that 10, I keep messing up on that 10. There we go. I keep hitting the 0 and it doesn't take. You guys probably saw that already. All right. Always go back and check your work. If something doesn't work out, just see if something silly happened. There we go. So Desmos gives us an integral, and our algebraic answer as a decimal work out completely. So I love it when a plan comes together. So you've now learned how to enter these equations into Desmos. If you've never learned how to use Desmos before, you can do an integration problem in Desmos, and you can check your work in Desmos as well. All right, so this is the end of video 1. I have video 2 and video 3. I like to keep these somewhat reasonable length, otherwise we all get a little bit bored. All right, see you in the next video.